Hey guys, it's AJ from Design the Everything. Today I'll be doing the 5th video in my series of videos on 3D printing a jet engine. Today I'm going to be talking about some of the thermodynamics behind how a jet engine works. Now my jet engine, like most jet engines, is going to run on the Brayton cycle. Technically an engine that uses the Brayton cycle is an open system. Mass goes in, mass goes out. Now that's hard to analyze. Fortunately, we can just treat the Brayton cycle like it is a closed system, and we just assume that the atmosphere is part of our system. Today we're going to be using that to look at some of the power output that our engine might have and its efficiency. Thermodynamically, the engine has 3 parts: a compressor, a combustion chamber, and a turbine. The compressor collects the air and increases its pressure. By increasing its pressure, it's also increasing the amount of oxygen that's in the same amount of space. So, when we go to burn the fuel with that oxygen, there's more oxygen available for the fuel to burn, making it more efficient. The compressed air is then passed to the combustion chamber, where it's mixed with fuel and ignited, which increases the temperature and therefore the volume of air. The extra air escapes through the turbine back into the atmosphere. While the air is passing through the turbine, some of the energy in the air is siphoned off to turn the turbine. Now the turbine is connected directly to the compressor via a drive shaft. So the compressor is powered directly by the turbine, which is powered by the air that's coming out of the combustion chamber. And the combustion is only possible because of the compressed air that's going to it from the compressor. It's that flow of events that makes the Brayton cycle engine a continuous process and allows it to keep going. A Brayton cycle engine, a jet engine, follows all of the same steps as a normal combustion engine: suck, squeeze, bang, blow. But a Brayton cycle engine has an advantage where it's doing all of these things continuously at the same time. If you go to a piston engine, and let's just look at one piston, it goes through 4 steps. It sucks, it brings in the air; squeezes, it compresses the air; bang, it ignites the air fuel mixture; and then blow, it exhausts. If you look at those 4 steps, only one of those is producing a usable force, the bang step. And one of them is actually even requiring force from something outside of the system. Normally, it's provided by the other cylinders in the engine or a flywheel, and that's when it's squeezing. So that means it's only producing force a quarter of the time, and a quarter of the time it is requiring a force input. The Brayton cycle engine does all of these things at the same time. So yes, it's requiring a little bit of force all the time, and that's in the compressor because the compressor has to be turned by the turbine. But at the same time, it is always producing a force in the combustion chamber. This means you can get a lot more energy out in a much smaller package. Let's look at the different kinds of efficiencies that are at play in a Brayton cycle engine. There's 2. There's thermal efficiency and mechanical efficiency. Mechanical efficiency is determined by things like friction and air resistance. And we'll worry about that kind of thing in a later video. Those are pretty straightforward to deal with. But the other type of efficiency is thermal efficiency, and that's what I really want to talk about in this video. The thermal efficiency of a Brayton engine is determined by this equation. The efficiency is equal to 1 minus the temperature at the inlet over the temperature of the combustion chamber. Now there are some other factors at play, like heat escaping through the walls of the engine and so forth. But we're just going to assume that those will be minimal in this engine. We're going to ignore those. But if you look back at the equation, there's only one part of that we can control, and that's the temperature in the combustion chamber. Granted, you might be able to put the engine in a freezer or something and control the inlet temperature, which would help efficiency, but we're going to assume that we don't get to choose the conditions this engine is running in. We're just going to assume room temperature, which is 20 degrees Celsius or 293 degrees Kelvin. We can, however, control the combustion temperature. The combustion temperature is based on a number of things. First of all, it's based on the type of fuel that we're using. It's also based on the quantity of fuel we're using and the quantity of air we provide. Now, I had a really hard time trying to figure out what temperature the isopropyl alcohol would burn at. From my research, the best I could find is that sitting in an open dish burning, it'll burn at about 400 C, which is 273 degrees Kelvin. If you use those numbers and plug them into the equation we talked about earlier, you end up with a thermal efficiency of 57%, which really actually isn't bad. That is actually higher than a normal internal combustion engine. Unfortunately for us, running at 400C results in a very melted and probably on fire engine. So we need to keep the temperature lower. Fortunately, we can pulse the fuel as it goes into the engine and pulse combustion. So sometimes it's burning, sometimes it's not. And if we do that right, we can keep an average temperature of combustion lower. We can keep it down at like 100 degrees C, which a 3D printed engine should be able to survive, at least for a little while. Now, 100 degrees C is 373 Kelvin, which you have to use Kelvin when we're using the equation I talked about before. So with these numbers, 373 in the combustion chamber and 293 at the inlet, our best possible efficiency, without even talking about mechanical friction or heat losses, is 22%. Now, 22% isn't very good, but we don't need this thing to power an airplane. All we're trying to do is get something that runs and runs continuously, and I think we can do that with a 22% efficiency. According to Wikipedia, our fuel has a energy content of 24 megajoules per liter, which, by the way, is a ton of energy. Using that, we can figure out how much power our engine can produce. If the engine consumes 100 milliliters of fuel in a minute, that provides 2.4 megajoules per minute. If you take that 2.4 and divide it by 60 seconds, you end up with 0.04 megawatts. 0.04 megawatts is also 40,000 kilowatts, which again is a lot of energy. But we are never going to get our 40,000 kilowatts. Even if all of the conditions were perfect in a lab environment, you would never get close to that much power out of the fuel. Now let's try to predict how much power we'll get out of this engine using our efficiencies. If we assume a combustion efficiency of 50% and a mechanical efficiency of 50%, and we know our thermodynamic efficiency is 22%, you get a potential power output of 2.2 kilowatts. That's about 3 horsepower, which would be a decent lawnmower. Now that is still a lot of energy, and frankly, I don't think that this engine will even do this well. But the fact that it could do that well is exciting to me. Think about all the things you could do with a 3 horsepower little engine that's the size of, 2 coffee cans put together. That's awesome. And we're going to be 3D printing this thing. Honestly though, I think our total power output of the engine is going to be about 10 watts. There's just no way we're going to get 2.2 kilowatts out of this engine. Where's our energy going though? Why don't I think that? Well, first of all, the combustion efficiency is directly dependent on the compressed air that the combustion chamber is getting. And remember, the amount of compressed air that the compressor is producing is directly dependent on the turbine. And the turbine is directly dependent on the combustion chamber, which is dependent on the compressor, and you get the cycle. Now, when you take a complicated cycle like this, they actually get pretty unstable pretty fast, and really unexpected things can happen. If there was no friction in the system at all, this would run away. This would explode, because everything would just feed back into providing more and more energy. The compressor would provide more air, which would make the combustion happen at a higher temperature, which would provide more thrust and more energy to the turbine, which would then just provide more energy to the compressor, and it would cycle until it ran away. But if there was too much friction, there wouldn't be enough air provided to the combustion chamber, which wouldn't provide enough air to run the turbine, which wouldn't provide enough air to run the compressor. And slowly it would wind down to nothing. Since we live in the real world, we know that the friction losses and the thermal losses will be way too high to keep it from running away, which makes me think that we're going to run into the opposite problem where everything's cycling down. Either way, I'm super excited about this project. This week, I really wanted to actually do a build. I wanted to test the efficiency of different shapes of fuel igniters. I've slowly been working on this rig, which is my fuel igniter test rig. It's super heavy in aluminum, and it has a really heavy, like 1-pound piston. And the way this is going to work is we're going to ignite some fuel in the bottom and then measure how high the piston flies. Hopefully not outside of the tube, but we'll see. So I'll make that as my next video. I don't know when I'm going to get it out. Right now, these videos are killing me, especially with work. But I will continue the series, hopefully until we have a working engine. Don't forget that I teach one-on-one Fusion 360 classes via Skype or Google Hangouts. If you are interested in one of those classes, please send me an email at the email in the description. It's those classes that help me pay for things like this mic. And look, I got a backdrop. How cool is that? And I have some lighting over there, hopefully really helping production quality. The other way you can support me is by using one of the Amazon affiliate links in the description down below. Just clicking on one of those links and buying what I have there, or buying anything from Amazon, gives me a small cut, which really helps me buy upgrades. That's actually what paid for this microphone and this camera. If you like this video, please hit the like button. And if you want to see the rest of the series as it comes out, go ahead and subscribe. I would like to say I do these videos weekly. That's my goal, but let's be honest, I do about once a month right now. Hopefully, they get a little bit more regular in the future. If you have a question, or if I said something wrong and you want to tell me, leave it down in the comment section below. I'll get back to you as soon as I can. And those also actually help the channel by boosting my rankings in the search results. Thank you for watching, and I really hope to see you next week.